All right. Hey, Internet. My name is Steve. You've probably seen my name pop up in comments, usually on YouTube or Facebook. I go by Steve, or probably seen me as Turbo 6 Detail. And I kind of wanted to go over foam cannons and how they work. There have been a couple videos that came out, especially with the new Active 2.0, or sorry, not the new Active foam cannon that was released, and there was a lot of investigation by a couple of channels, good information that they found actually, and that actually helped with this video. So we're trying to figure out how foam cannons work and how they, why one cannon will foam more than the other. Why does the MJJC foam more than the MTM? And I'm picking these two because they're on opposite sides of the spectrum, so it should be really easy to see what the real differences are between them. And so, I'm an engineer by day. I spent a good part of my career reverse engineering parts for the automotive industry, and at the current moment, I work in with pipeline design or pipe design. So this kind of fits in my wheelhouse of I don't want to say expertise, but because I'm not like a equation theoretical guy, but I've done this for my job. So we'll get into it. It might get a little technical, and if you want to just get that endorphin rush and the answer really fast, I can tell you right now why the MJJC foams more than the MTM, and the answer is it's in here, right in here. There is a small orifice that is responsible for siphoning, the soap out of your bottle, and the orifice in here is smaller on the MTM than the MJJC. The MJJC has a larger orifice. It takes up more soap. And what I want to express here is that it's not necessarily a better cannon, right? What makes a good product, it's not a better foamer. It's just has a different restriction. The cannons are doing the same thing. There's no difference with how they work. The action is the same, but on the MTM, you have to run a bit more concentration of a mixture because it does pull less, right? The MJJC will empty its bottle much faster than the MTM. The MTM is drawing less fluid, less soap. So, that's the answer. Now, if you want to learn more, stick around for the rest of this video. If not, go about your day. You got your answer. See ya, right? I can't leave it like that. I need to figure it out. That's just how I am, and I can't help it. So I started off with looking at the cannons themselves, and what we'll do is we'll change the scene here, and I took a microscope, and I took a microscope and pointed it down into the MJJC and the MTM, and what I did was I made sure that when I took these photos, I did not change the focus point or the focus of the microscope. So once my object was in focus, I know that at that point, the images they'll be able to be compared, right? It's a fixed focal point. So this is a technique I've done for parts in the past. Maybe there's a difficult angle to measure. Using a camera and overlaying images, you can figure out a lot of geometry this way. So it's a relatively reliable way to compare things. I didn't measure the orifice, but you can see that my photos are pretty consistent in terms of focus here. So this is inside the MTM, and you can actually see there's a bit of a different type of corrosion happening inside the MTM than the MJJC. But here you can see that orifice inside the straw tube, right in the middle of the screen here, and you can see the vent. And on the MJJC, it's the same thing. Here's our vent off to the left. The MJJC, it seems like the orifice sits a bit deeper into the Canon, but in terms of taking these photos, they are the same length from the microscope lens, right? And what I did was, now I'm not like not a Photoshop guy, right? So I went into my Canva here and I put them together, right? And if we add, so we have the MJJC here, you can see the blue. And what I did was I took this image and added a bit of transparency to it, right? And when we bring them together, and let me put the MJJC further into the middle of the screen, and you can see I didn't change the size of the photos, I didn't change the scales, nothing has changed here, they are very consistent. When we overlay them, it's really obvious here that the MTM has a smaller orifice than the MJJC, right? You can see the ring almost kind of like an eclipse right in the middle of the screen. So if I take it and we'll just make it somewhat tangent here over, you can see how much extra open area there is in the MJJC. And this is part of what's responsible for the extra suction. Now, we're calling this a siphon orifice. I'm calling it that because that's what it is. It's an orifice in the siphon line. You know, the way a Canon works, there's no moving parts, right? And it's all based off of something called Venturi effects, or a Venturi effect. Some people call this a Venturi siphon. If you go on YouTube or Google, look up Venturi siphon, and you'll find so many examples of this principle at play. So what I've done here is, and you know, this is the part where we get to learn a little bit more about, you know, how the Canon works, right? So I've drawn up a really simple diagram here of, you know, what is happening inside a Canon and what would affect how you draw out soap, right? So we have our, and I'll turn on my little laser pointer so I don't accidentally, does that work? Hopefully you guys can see that. Right here, this here is our inlet, right? We put a quick connect there or hose or whatever. This is our inlet. Right here is our orifice, right? And this is the one that we switch out a lot, right? Say you're running a Ryobi pressure washer. You'd use a 1.1 orifice. If you have something larger, you use a 1.25. But if you take a Ryobi pressure washer and run a 1.25 orifice, you'll notice that you actually get less foam. And there is a reason for that I'll go over, right? But let's just get through the diagram first. So yeah, this is our orifice. And then in green here, I've drawn in another orifice. This is our suction line right here. Normally, this is the lid, and you'd have your bottle hanging off the bottom. So I wanted to make sure that we highlight this orifice so that you know where it's at and why it's important, right? So everything leading up to that orifice is wide, and then you have this orifice here, and you have an empty space here, right? Up here would be your knob, typically, right, that adjusts your foam and how much foam is coming out of the Canon. But this right here, we'll call it a mixing chamber, right? Because that's exactly what happens. That is where your pressure washer stream of water meets your foam mixture, or your soap mixture, right? And then we have, you know, the typical some sort of assembly down here. Your screen is usually out here, right? And we exit the Canon this way. So what I'll do is, just so that we remember, we have water in, and then we have our, I guess we'll use foam out, right? And up here is where our soap goes, right? Normally we'd have our big straw down here, right? That's siphoning up your soap. I said earlier that there's no moving parts. There isn't. There really isn't. The way foam cannons work is they use a Venturi effect. And what that is, when we bring water in through this nozzle right here, and actually I'll go blue here. When we bring in water at this nozzle, the purpose of this nozzle here is to increase the velocity of the water, right? Excuse the handwriting, right? We want to increase the velocity, and that's important. When we get out here, right, that stream of water generates a quite intense vacuuming effect. It's a pumping effect, right? So as it comes through here, when water passes over an opening, or if you have a stream that passes over an opening, it generates a vacuum. It generates a suction force that allows, the soap to be drawn up through the straw. And right away, no matter what tip we use here, we can understand that if two foam cannons have a different size orifice right here, right? Let's see if this diameter is different, then they'll draw up different amounts. If everything else is equal and the only thing that changes is this orifice, they'll draw up a different amount of soap, right? And that's what we're seeing with the MTM and the MJJC, is that the MJJC orifice is much larger. Now, we also know that depending on the size of this orifice, this is the one that we can take out and replace, we know that when we run a larger orifice, we get less foam. When we run a smaller orifice, we get more foam. And why is that, right? So that is due to, again, I think this is more of a Bernoulli equation thing. I can't remember offhand. Bernoulli equations and Venturi effects, they kind of go hand in hand. But what happens though is we have a big pipe. We'll call it we'll just call this a big pipe, right? So we go from big pipe to small to big again, right? When we're putting water through here, we're going to assume that we're putting in the same rate. So no matter what happens, let's just say, because it's a common number, we have 2 gallons a minute going through here. No matter where you are in this pipeline, you have 2 gallons a minute going through. So when we look at this diameter in here, right, it's actually moving, even though there's more pressure. So big, we have more pressure, but less velocity. That's really important to understand, because for our Venturi effect to work, we need velocity. And the smaller orifice generates more velocity, which in turn generates actually more suction, right? And you can see this whole effect with just taking your pressure washer. When you take off the nozzle and you pull the trigger, it just comes out like a garden hose, right? We have a very large orifice, essentially none, and it just kind of spills onto the ground. When you put your nozzle onto the end of the gun, suddenly we have a very small orifice, and the velocity of our water increases. So if we slow down this velocity, right, this inlet velocity, we also affect the suction. Now, um, you know, common sense or whatever you want to call it, or intuition says, well, then just run the smaller orifice, right? Run the 1.1. If you have a high GPM or a high output pressure washer, running a real small orifice it can damage the pressure washer. So manufacturers are balancing whether do they want you to have more foam or do they want to protect, your $350 plus, or $650 pressure washer. They're usually going to pick the pressure washer. Most of us can deal with not having perfect foam, right? So that's kind of the big effect here, right? If we slow the stream down, we're going to get less suction out of the foam cannon bottle. If we speed it up using a smaller orifice, we'll get more foam. And it's so evident on the Ryobi because the Ryobi, the 1.2 gallon Ryobis, when you start opening up the orifice, it loses a lot of, since it's a smaller volume, it loses a lot of velocity. So it becomes very apparent. There's a difference, but with some of the larger pressure washers, you might not see the whole difference between a 1.1 and a 1.25, or maybe a 1.25 versus a 1.3. You might not really see a difference in foam, but it would help the longevity of your pressure washer. So as I was saying, though, when we have a big, we'll call it a big diameter pipe, we have more pressure and less velocity. When we get to a small area like this one here, right, we actually have less pressure. And as you guessed, more velocity, right? We've kind of been saying this already. Now, this is a really important concept, as I keep kind of repeating myself that this is an important concept to understand. Especially when it comes to measuring pressures and whatnot. So if we were to put a pressure gauge right here and read it, a pressure gauge here and read it, this pressure gauge will be high. So we'll just say that that's a high number. This one will be lower. But what happens out here when we return to the big size, right? Well, we go back to higher pressure. But you'll notice that I'm not saying it's the same pressure. We'll have less velocity, right? And we see this on the foam cannons all the time. The stream that comes out of a foam cannon is not going nearly as fast as the stream coming out of a nozzle, a pressure washer nozzle, like a 25-degree tip nozzle. So we can observe that. We see that. But what happens to the pressure here? And what actually happens is we see pressure again. Now, when we're going off out into atmospheric, maybe it's a little bit different. It shouldn't be. But there's a lot of things that happen in this third chamber here, right, that could affect pressure. So we're going to just ignore that for a moment here, and let's just stay with just a pipe. This is a very simple diagram. We have pressure, but typically you'll see this. It won't be as high as that first one. It actually will be slightly lower. And that's something called pressure drop. And we experience pressure drop every single hose, every single pipe, every single tube. Anytime it has a bend, an elbow, a fitting, a restrictive orifice, it experiences something called pressure drop. And it's a fundamental concept in pipe design. And basically what it says is that, as water traverses through a pipe and hits all of these restrictions, like elbows, like I said, elbows, nozzles, fittings, it experiences a lot of friction. And that friction can be seen later on in the pipeline as a slight pressure drop. So I'll probably make another video that goes over that. But it's just one of those things where understanding, really it's these first 2 points for foam cannons that's important to understand, right? When we close this up, we increase the speed, we actually see less pressure, but that velocity is what's used to siphon out into a foam cannon. So if now that we know this, I feel like this would have been fun as a live stream. So what I'm going to do is I'm going to draw our bottle in here, right? So let's do, yeah. And we're going to do a simple bottle, nothing fancy here, right? And it has some sort of liquid in there. So on the photos, we talked a little bit about this vent right here, right? And the reasoning for it. And Active, and I haven't gotten my Active yet. I'm hoping to get it in a couple of days. They said that they solved the spilling issue. So why do pressure washers even have that vent, right? Why do we need this vent right in here? And you notice that I'm calling it a vent because that's kind of what it is. It allows, so as we siphon, right, think of this as a vacuum cleaner almost, this line right here, right? So we have water getting siphoned up through here. That means at some point our water level here is going to start to drop, right? So our water level, maybe it's down here, right? Well, we have air in here. All this empty space up here is air. So if we were to drop the water level, we need to allow air into the bottle so that we don't create a vacuum, right? Because then we'd have two vacuums. We'd have a vacuum up here, you know, pulling our soap out. Let's do that again. We have a vacuum up here. That's pulling our soap out, but then you'd have a vacuum working against that down in here, right? If you didn't have this whole area down here, it'd be a vacuum. So you'd have two vacuums pulling against each other. You'd probably choke out the flow. It would stall, and you'd see a decrease in performance, right? And this is assuming that the lid is just perfectly sealed. We know that's not true. That doesn't happen. So why do they make it a hole? Really what they're balancing is how much, you know, if it was a big, right, if it was a big hole up here that just ran through your lid, sure, it would be able to let, you know, a ton of air in here, lots of it. But then when you shake the bottle, it spills, right? It spills out. So what they've done here is they've said, okay, well, this is the minimum size hole that we need to let air in at the right rate so that we don't choke out the vacuum, but also so that we don't constantly spill a lot of product, because nobody would like that. So I think what Active may have done, and you know, like I said, I'll have it in a few days, is in here they may have done something called a check valve, right? Which would say it would let air in, but stuff coming out, no, right? It's a one-way valve. Sometimes this can be in the form of a ball, possibly. I don't know what Active did. This is just a guess. There's two ways to kind of do this. There's a few ways, but this is my guess. You have one way, which is a ball that sits in here, right? And when the ball drops, it lets air pass through here, no problem. But if you were to flip this whole thing over, that ball, right, if this whole thing were to fill up with water, that ball would stop it, and it would block the hole that's sitting up there. So that's one way a check valve works. Another thing that they can do is they can put a diaphragm here, kind of like what you see when you fill up maybe some camping gear or something, or a pool, right? And they have like these little rubber diaphragms, and what that does is when there's a vacuum, all of your, I'm using different colors, I know, your air will come in. This will kind of bend out, right? Because it's just very flimsy rubber. It'll bend out a little and it'll let air in. The second there's no more air flowing through this channel, right? If you stopped using your gun, or if you flip this over, this kind of seals up against the bottom side of the cap. Again, it's a guess, but those are kind of the common types of ball valves that I've seen, or check valves, right? But the whole concept here, whether it's a ball, diaphragm, spring-loaded mechanism, a gate, or even it could even be a special manifold. I think the whole point there is that it lets air in, it doesn't let anything out. So we'll see, though. We'll see what that prediction looks like in a couple of days. But that's foam cannons right there. Oh, I didn't go over the knob, right? So the knob, we know that on the bottom here, this area is all dedicated to vacuum and siphoning out that soap mixture. The reason a knob induces less foam is it lets air in through the top, right? And it's an induced vacuum leak, right? If you look at the top of your the MJJC, it's very easy to see. When we twist this knob, all right, and I'll let's go over to the camera here, make this a little bit bigger. When we twist this knob, this is fully open. It's moving this direction, right? And you'll see these little vent holes here, right? And if you look inside there, you can actually see the plunger moving in and out, and it's just letting air in. That's all it does. So what it does is it breaks that siphon force. All of your vacuuming from that flow, when this is closed, is going through here. When you induce a vacuum leak by opening this valve, you let air in, and it can no longer siphon nearly as powerful on the other side. And that's how that works. The end of the cannon from here on out is all dedicated to aerating your soap mixture with the stream. So I'm not really going to get into that, mainly because I don't understand it, right? We have an O-ring here and an O-ring here, and this whole, from here to here, this whole space is a dead space inside this cap. It doesn't pull from anywhere, right? If we look in, it's literally just a solid piece of plastic with the screen on the inside. So I don't fully understand what these holes are for and how it plays into the rest of the cannon and the performance of the cannon. This right here, both the MTM and the MJGC have this. This is for when you put your cannon on here, right? You have the hole for the pin. When the pin goes through there, it sets in there, and that's what locks the end of your cannon on, right? So when you put your pin through, it goes through just like that, right? And then you can't, as I drop sharp things, you can't lose the end of this. So not going to like I said, I'm not going to focus too much on that, only because it's a piece of the puzzle that I don't fully understand. One thing that I have figured out is that both the MTM and the MJJC have some sort of conical, profile when it exits the mixing chamber in this manifold, has a conical profile that just happens to be about the same size as the screen on the inside. So I have a feeling that this is just for expanding your flow so that you utilize the full surface area of the screen. So anyway, that was the technical part of this discussion. I hope you enjoyed it. I enjoy breaking things down like this. Like I said, I'm not like a math theoretical kind of person, but I do have enough experience to know how this stuff works. And if you have any questions, shoot them over, leave them in the comments. If you like seeing this, let me know. If there's another, thing that you want to see broken down like this, let me know. I've done some of my own testing on things, like when a manufacturer or somebody claims something, before I bring it out to clients for detailing, I need to make sure that it works and does the thing that it says it's going to do. I hope that I was able to enlighten you just a little bit on how these work and why we see more foam out of one or the other. Personally, like I said, I'm not a product reviewer, but when it comes to foam cannons, I do value build quality, right? So, I don't want things coming loose. I do like, hear that? I like clicks, right? Something, the MJJC foam's great, but if this knob moves a little and goes off to another position, it changes my foam consistency. So that's just one of the things that I look for is build quality. Actually, I would be willing to bet that if you drilled out that orifice just a little bit more, you would get similar performance to the MJJC, but you're going to use more soap. So anyway, I hope you enjoyed. Comment, subscribe, like, whatever you want to do. It doesn't matter. I just enjoy doing this. This is just for fun, and I hope to see you again soon. Thanks.